We are going to look into the Lee-Carter model, which is one of the most famous stochastic mortality model. There are a few factors that lead to the mortality improvement in the recent years. We can see that the life expectancy is actually increasing in these recent years. Higher longevity or higher lives than expected leads to the increase in the value of the annuities. So, underestimations of the cost of the annuities will lead to loss to the both insurance company and also to the policy holders. This will impact more to the companies, especially those that provides whole life annuities. Therefore, good mortality models may help to reduce these issues or this problem. To analyze the potential impacts of random variations in the year-to-year mortality experience, we may use a stochastic process to model the future mortality experience. For a stochastic mortality model, it is a stochastic process for the rate of mortality experience by lives at different ages for different future dates. For this, we generally use the discrete time stochastic process so that we generate stochastic mortality rates suitable for each age in each future calendar years. There are few models that are quite reasonably famous. One of it is the Lee-Carter. Another one is CBD. What we are going to look into now is the Lee-Carter model. This model defines the force of mortality, which we usually use as mu x. We define the mu x as the central death rate with a notation of mx. Central death rate. For this, we are going to use the notations of mx, where your mx is defined as qx over integrations from 0 to 1 r px dr. This is can also be written as integration r px mu x plus r dr over integrations from 0 to 1 r px dr. For here, your mx is the weighted average of the force of mortality between age x and x plus 1, between this integral. If the force of mortality is reasonably flat, so that means that in between this integer, usually we have like mu x plus r. In between this integer, for each of the r here, your mu x plus r is reasonably flat or almost constant. Okay, so for this, your mx will be almost equals to your mu x. Thus, you are going to have qx equals to, or not equals to, it's almost equals to 1 minus e negative mx. Okay, in this model, the central death varies for age x and for the calendar year t. So we denote the mx as, instead of just mx, we denote it as mxt, where this one is for different age and this one is for different calendar years. And we assume that the log of the central death follow a discrete time stochastic process, where we have log of mxt here. This is equals to alpha x plus beta x kt plus e. I'll write it nicely. E xt. For this model where we have alpha x and beta x are parameters which only depends on attained hx, and we also have another parameters which is kt. This kt it includes all of the value for all of the t's. For the past values, the parameter found by fitting the data to the model. For the future values are modeled as a time series that fitted to the estimated historical value. You also have to know that this kt is not dependent on age. And the usual forecasting model is a random walk with a drift. So we have, for here, the random walk with a drift, we have kt plus 1 would be equals to kt plus c plus sigma k zt. This is the random walk with the drift. Okay, where for here we have c is a constant, and then sigma k is the standard deviations of the annual change in kt. And we have zt, where zt is assumed to be IID, which is independent and identically distributed random variable with standard normal 0, 1 distribution. Okay, this is what explain what kt is. And the last one in the model we have ext. This is representing the error. Let's rewrite this. ext. This is representing the error term, which we usually ignore. Okay, that's it for part 1 for the Lee Carter model. We are going to continue in the next video. Thank you.